Okay, let's go through and just demonstrate that the formulas I'm giving are exactly the formulas that R is using when it performs its calculations. So I'm going to use the diamond data set, and that's in the using R library, so I'm going to load those. Define y, x, and n like I always do with this data set so I don't have to type so much. My beta 1 is the correlation between the y and the x times the standard deviation of y divided by the standard deviation of x. And my beta naught is the mean of the y's minus beta 1 times the mean of the x. My residuals are my response y minus the predicted values, beta naught plus beta 1x. So here I've just carried the subtraction through. There's my residuals. My estimate of the standard deviation around the regression line, the variability around the regression line, is the average of the residuals, except remember we're dividing by n minus 2 instead of n, and to get it to be a standard deviation rather than a variance, I'm going to square root it. There's my sigma. That's my estimate of sigma from the previous several pages. My sums of my squares of x's is just the numerator of the variance calculation, but let's just do it directly. It's x minus its mean squared and sum of adding those up. So let me get that. And then my standard error for my beta naught for my intercept, if I just simply plug into the formula, there I've written it out. And my standard error for my beta 1, which is I think the more useful and mentally important formula to commit to memory, is the sigma, the variance, the standard deviation around the regression line, divided by the sum of the squares of the x's, the sum of the squared deviations of the x's around their means. Okay, there we go. There's the standard error for beta 1. I'm going to create the two t-statistics, which if you're testing a hypothesis that beta 1 is 0 or beta naught is 0, then that's just going to be the estimate. Here's my estimate, divided by its standard error. And so we don't have to subtract off the true value because the true value is assumed to be 0 under this hypothesis. And so for my beta 1 hypothesis, it's going to be beta 1 divided by its standard error. And then I'm going to calculate my two p-values. Again, if you've taken the inference class, then how you go from a t-statistic to a p-value should not be a great leap. But in this case, it's going to be twice my t-probability, where in both of these cases the estimates are larger than 0, so I'm going to look at the probability of being this statistic or larger, and I'm going to double those two t probabilities. And then I'm going to create my coefficient table created manually by me without having done any LM or any built-in higher level R function. And I'm going to give it its row names and its column names so that it looks like R's output. And then now I'm going to show you the easy way to do it. Okay, so here let me print it out. There it is printed out. And then now I'm just going to do fit LM, my response Y, is a linear relationship with my predictor X. And then I'm going to get the summary of the coefficients. You'll see everything is exactly the same. So if you didn't follow all this, it's not too big of a deal. I just wanted to show you, for once, that the formulas that I'm giving you are exactly the right formulas, and we verified them computationally by checking them out on a data set. Maybe check them out on another data set just to verify for yourself. Let's go through getting a confidence interval. So my fit, the variable fit, was the output of LM. Let's see what happens if I type summary fit. You get the full output from LM. So it gives you facts about the residuals, it gives you the coefficients, the estimated coefficients, the standard errors, the t-values, and the associated p-values. These are all for test of whether or not the intercept is 0 or the slope is 0. Now, of course, a 0 intercept may not be of interest, but almost always a test of a 0 slope is of interest. But it also gives you the residual standard deviation, the degrees of freedom, the R squared, the adjusted R squared, which we'll talk about later on in the class. Let's go ahead and generate our confidence intervals for our intercept and for our slope. So now I've assigned that summary the summary from the LM statement to an object in R, but I just wanted the table part, so I'm grabbing just the coefficient. So it's right here, see, I'm just grabbing the coefficient table. So let me just print out that variable just to show you what it looks like. It's just the table part, just the estimates, the standard errors, the t-values, and the p-values. Okay, so our confidence interval is just going to be estimate. So here's for the intercept, estimate plus or minus the 97.5th t quantile with the degrees of freedom, just to make sure I get the degrees of freedom right, so I don't even have to think at all. I'm grabbing fit $ degrees of freedom, and then times the standard error. There I'm grabbing the standard error. And then I'm doing it for the slope, which is in the second row of the first column. So the slope estimate plus or minus the relevant t quantile times its standard error, which is in the 2-2 cell of this table here. And then the slope is going to be interpreted in change in Singapore dollar price per 1 mass increase in carat, the unit for the predictor variable. But I might want it for a 0.1 increase because, as we mentioned earlier, looking at the data, a 1 carat increase was kind of a big increase. So why don't I divide my whole interval by 10? So let's run both of them and particularly focus in on this latter one, the confidence interval for the slope. So it's saying with 95% confidence, we estimate that a 0.1 carat increase in diamond size is going to result in a 356 to 389 increase in price in Singapore dollars.